Today our topic is of course not algebraic graph theory, but one of my favorite topics. Like it's like you wake me up in the sleep and you ask me also, I'll just tell you anything and everything about this topic. Okay, it's like that. The topic is, as you can see, it's about interconnection networks and Cayley graphs. Interconnection networks, maybe now this generation of people, I don't know if you have got a chance to know about this. I guess not, right? Because now you are in a world where you are in, like, you are handling scale free networks. You don't have anything bound kind of thing. You don't bother about how the connections are made, okay, or most of the time we will be talking about a grid structure, right. So this is kind of when parallel processing, about parallel processing and parallel computing started, interconnection networks had the highest fame. Okay, even now we try to connect the networks to the kind of other problems that we do, and we try to study these networks and their properties. So the introduction, I mean, just I'll try to cover as much as possible here. This is like, we'll talk about origin of the problem, where what kind of problem is there, was there, at least I should try to tell you that, and the modeling, and we'll try to touch upon about two specific interconnection networks, and then I'll go into a generalization of these networks, which is called as the Cayley graphs. So the origin of the problem, it started with you, if you have a parallel algorithm and you want to, and you also have a parallel computer in hand, you want to execute your algorithm in the parallel computer, right. So now everybody is doing it from the cloud. So you upload your program in the cloud and you just don't know what the cloud does, but the cloud actually takes care of these things, because when you implement, it has to give an equal share of data to every server that it is having, right. You cannot just like that occupy one full server to run your program. So usually it will be parallelized and it splits the data to multiple computers, and then the computation is done. And in this process you will also have to collect the data. Once you split and give the data, you collect it back and how you combine them. So all these kind of studies were done in this field. So what is all these terminologies? So you all know about these things, a collection of processors. Okay, when we say a supercomputer or a parallel computer, what we mean is you have a collection of processors. They are interconnected in a very specific pattern. Okay, that pattern is what we call as the interconnection network. How these processors are connected between them and how the communications can happen. So the network, underlying network, is called as the interconnection network, and we assume, I mean, there is a standard assumption that we make, like every processor is capable of doing the same job. They are equally likely. Okay, otherwise you can also think of, if you have a quad core in one processor, octa core in the other processor, then you know it can do different jobs. So you have to also, you can also give different loads for the processors, right. But for our purpose, we will fix that all the processors are equally likely, that anything can do any job in the same fashion. So what is the problem that we have? You have to design a parallel computer to function as originally designed, even in the presence of failure. So actually I have gone one step further. Instead of talking about just running a program in a parallel computer, you should also think about the design in such a way that even if there is a processor failure that is happening or a connection failure that is happening, still your program should be running in that parallel machine efficiently, right. So this is one problem, and this problem is still a very current, I mean, what to say, a hot topic which requires a lot of addressing, because failures can occur. You are working, suddenly your power cut happens, and then you don't know where your program was running, and you have to restart and redo the whole job, right. So still now we have a lot of, at least in India I can immediately say that we have a lot of trouble with this fault tolerance issues, like communication network failures can happen. In that case, how do we overcome this situation, right. So how do we overcome if there is a presence of failure of some processors or links or both? Okay, in that case, how will I redesign my algorithm or my computer? It should work. It should know automatically how to reroute itself, its connections. If suppose one processor fails, it should be automatically rerouting the connections, that so that leaving this, all the other elements which are connected to this particular processor should also be connected, and the communication should happen without any hindrance, right. And this hindrance, for the user, he should not realize it. That is the major thing. Even though there is something happening at the back end, the realization, I mean, within fraction of seconds you expect that the whole thing gets restored. Okay. So, how can we do this? So, this is one big problem that we face these days, that is about fault tolerance, study of fault tolerance, and this study is also there for a long time. People are trying to overcome this issue. One way of overcoming this is you also design your system with survivable routing techniques. So, you give a routing technique to the computer, so that in case if there is a fault tolerance, that is a fault that is occurring, then system will automatically reroute it, and it knows how to reroute, and it can run the programs, right, programs, or it can continue to do its job, whatever it was doing. Okay. So, the problem now comes to just running this parallel algorithm on a parallel computer. In case of failures are also there, if there is a failure, then we will have to also address it. If it is not, we are just going to run the algorithm in the machine. So, how do we model this problem mathematically? So, your interconnection network, it models naturally into a graph. So, where every processor becomes a vertex, and any two wires that are connecting the processors, the communication between the processors are going to be modeled using edges, right. So, graphs are the natural model for your interconnection networks, or any networks nowadays we can model them, right. What about the other end? Given a parallel algorithm, how do I run it? For the parallel algorithm, what we do is we look at the algorithmic graph. What is an algorithmic graph? Flow of the program that you have. Okay, you call it as algorithmic graph, where how your data gets split up and what kind of process that needs to do, right. Suppose I give you a sorting problem, you want to run it in a parallel machine, right. Say you have an 8 processor machine that you want to run, and I give you say 8 digits, 8, I can even give you more than that. So, what we try to do is we usually do this binary sorting. You just keep splitting the data into 2 sets, send it to the 2 nearest neighbors, and they will send it further. So, you kind of have a complete binary structure where data gets split, and the last level they will get like two inputs at a time. So, sorting 2 elements is easy, right. Given n elements, out of n elements, sorting 2 elements becomes easy. You just check whether this is greater or this is greater, and you just rearrange them and you send back the output. So, this is a hierarchical structure. So, this kind of structure we call it as algorithmic graph or data graph. How the communications are going to happen, if my data gets split, and how will it get connected back, how do I get the final output, right. So, this whole process is what we call as computation graph or algorithmic graph. So, the problem now to run the algorithm in the computer is nothing but you have to find a mapping of the nodes of this algorithmic graph to the nodes of my processors. So, if I can give a one-to-one mapping or whatever kind of mapping that we are targeting on, if I give a mapping, then this algorithmic graph, whatever is there, it is kind of an ideal case for us. This is how my program should run, right. So, if I can embed it, or if I can find this mapping, then I know my processor will replicate its job and it will do the computation effectively, right. But the problem here is to find this mapping, map the corresponding algorithm graph. So, that finding the mapping is the biggest problem, and there are lots of studies in this. When your algorithmic graph is a different class, there are various possibilities. Like for example, if I talk about sorting, I can just do a binary split and I can give you a complete binary tree as a data set. Similarly, processors can change, right. Usually our algorithmic graph will be a tree structure. It takes one of the tree structures, I mean not always, but at least it is a very good start we can think of. You either divide the problem, divide and conquer techniques go in that fashion, right. You divide the problem into sub problems, you distribute it, sub problems will be individually executed in these other processors, and that what will it do? It will again split the problem into sub problems and send it to its children, right. That is how the processing happens. So, the algorithmic graph takes a flow naturally as a tree structure, usually complete binary tree or any k-array tree we can think of. So, about embedding, so to formally define what I am talking about mapping, the map that we are talking about is nothing but you have to find two functions f and rho, where f is a mapping from v to w and rho is a mapping from the edge set. Okay. The edge uv is getting mapped to a path connecting f of u and f of v. Okay. So, that is what your rho is going to say, because I might not be able to guarantee an edge to edge embedding, right. So, I give you a relaxation even though my uv edge in my algorithm graph is a, I mean u comma v, it is an edge here, I need not map it to an edge, but at least they should be connected by a path. Okay, I cannot just map it in two different components. If there are two components, I cannot map it in two different components and say like this is a mapping, right. And most of the time for this path we will consider shortest path. There may be more than one path possible, but still we will consider only the shortest path connecting f of u and f of v in the processor graph. So, now translating everything into our graph terminology, my G I do not hereafter call it as algorithmic graph, I will just call it as guest graph. I have a guest, I have a host, I want to embed my guest into the host graph. So, a simple language. So, this is what is an embedding. So, to give you an example, just consider this G and this H. Okay. So, I have just given you a mapping where the small word alphabets V1, V2, V3, V4, V5 are mapped into capital alphabets here. Okay. So, you can see that V1 here is mapped to this node here, V2 is mapped to this node again, V3 is mapped to this, and V4 is mapped to this node, V5 is mapped to this. Right. So, this is a embedding. Okay. In fact, there is one trivial embedding. Can you all think of that? Trivially, if I give you a G and a H, I have not told you any other condition about what f and rho should be, right. I can just take every node of G and put it in one single node of H, right. But that is not so good for us, because we are literally defeating the purpose of having a parallel computer. Instead, we are just using one processor to do all the job, right. It is like you are running the program in one single processor. Even though you have resource of 10 processors, you are doing it in one processor. So, in that sense, we need to find an optimal embedding. Okay. So, optimality has various parameters here again, like in the previous session we saw some 7 parameters, right, centrality and all. Here also we have similar thing, like we should consider there are two things, right. So, on my processor, what are all the facts that I should consider? If I embed G into H, I should be cautious that I am not going to overload a particular processor, right. In my embedding, I should be cautious about that part. So, we would not like to want to have an embedding like this usually, but unavoidably if it happens, we can of course find a mapping like this. Okay. So, we do not want to overload a node in here, a node or a processor in here, that is one thing. And also when I try to embed, say V1, V5 has a connection here, that means what? If suppose it is directed, once V1 has done its job, it is going to send the data to V5, right, or vice versa. Anyways, now I have given an undirected graph, but suppose V1 sends it to V5, here what should happen? The same communication should happen. So, from V1 I should send the data to the corresponding V5 here, right, the mapping of V5, right, f of V1 and f of V5 should be connected, and if it takes long time to communicate, then it is again a little bit of lag you get to see, that is called as a dilation, like how much you have dilated your single edge into path, right. So, you want to look for a path which is like the shortest possible path, that is the reason we go for shortest path. And there are also other parameters like congestion, we say network congestion or traffic congestion, right. In roads, if you walk, you know how much traffic is and how much congested the road is. After a certain limit, you know you cannot move anything, you cannot move at all, right. So, if that happens, then we are in trouble, right. So, congestion in the sense like, say suppose if you look at this V3 node here, this is kind of highly congested. So, every path connecting V1, V2, V4 has to go through this V3, right. So, that in that node is going to do a lot of job, and if jobs keep coming into the processor, it has to wait. So, that okay, I will finish this job, send it, then I will take up the next job, in queue I will do this one, right. So, congestion is one other factor. This is called as node congestion. Suppose if I look at this edge V1, V3, this edge is also again congested, right. Every path contains this edge. So, that edge is again highly congested. So, this is called as edge congestion parameter. So, we want to minimize these factors, minimize dilation, minimize load, minimize congestion in the network. Along with that, there is also another factor which is called as expansion cost, that also we need to minimize. Okay. But the problem is you cannot do all those things simultaneously, even though all are looking like minimization problem. Okay. We cannot simultaneously do it because the network has its own limitations. Okay. Our embedding also should be proper, that we should take care of it in a proper fashion, right. So, what will be the ideal case for an embedding? So, minimum load is load, if I say minimum, that means what? Every processor is going to be used at most once. Dilation is minimum, means what? Every edge goes to an edge, that is an ideal case, right. In that case, congestion is also going to be minimum, because every edge is already mapped to an edge. So, there is no congestion factor coming into picture here. So, every edge has equal congestion there, right. So, the best possible embedding that we can look for is the subgraph embedding. Okay. So, can I put this graph into this, so that there is a subgraph, a copy of this as a subgraph in this H, right. That is one natural question we keep asking. So, coming back to our problem, what are the possible host graphs are there, right. So, host graphs, if you see, there are, these are some of the standard host graphs we have been working with. The linear arrays are nothing but the meshes or grid structure that you have, right, and rings or torus, right. These are also standard structures that you have seen. Star graphs or hypercubes. So, that is what we will talk about today. After hypercubes came, hypercubes literally took over a kind of 4 decades completely, 40 years was ruled by hypercubes, I would say. After 1960s, 70s, they started until 2010 also. There are, even now you open, you will find a paper on hypercube getting published. Somehow hypercubes they have a lot of property, you will see why they rule the whole community of networks. Okay. And then we also have generalized hypercubes, a generalization of the hypercube structure, and then there are also other variations of hypercubes like folded cubes, twisted cubes, and there is also one more beautiful structure which I have not included here. It is called as cube connected cycles. Okay. That is also another interesting structure. It has very beautiful properties. So, we will try to see if possible after we do this. So, coming to our hypercube. So, let me start, because other things you know, torus, grid and all. So, let us start with hypercube. So, an n cube is an undirected graph. It consists of 2 power n nodes. If we are talking about an n dimensional hypercube, then I say it has 2 power n nodes. So, number of vertices itself is exponential. So, let us not worry about exponential part, but whenever we talk about algorithm and its time complexity, anyway we are going to talk in terms of order of n, order of 2 power n. So, whether it is polynomial in 2 power n or not, that is what we will be worried about. Okay. So, how are the edges going to be connected? So, first of all, vertices have an n bit binary string labeling. So, zeros and ones, you have n bit labeling, and any two vertices is connected if the labeling differ in exactly one position. Okay. So, this is a standard definition. So, these are some basic cubes that you have already seen. So, still I have given you here. So, you have 0 1 is the first cube, q1 of dimension 1, q2 is nothing but 0 0 0 1. You can see the edges, they follow the pattern, like they are adjacent if and only if they differ in exactly one bit position, right. Similarly, q3, right. So, there is also another alternate definition for this cube. Instead of looking at it as binary just labels, as mathematicians we always like to add a structure on top of it, right. So, there is the other structural definition for this using the Cartesian product. Already I defined what Cartesian products are, right. You take two tuples, two vertices, if you have two graphs, every graph is now G cross H is going to have vertices as tuples, right, u comma v. Say u dash v dash is there, then you join two vertices if either u is equal to u dash and v is adjacent to v dash in my h, the second graph, or u is adjacent to u dash in the first graph and v is equal to v dash, right. So, this is the standard Cartesian product definition. So, if I try to translate this into our binary string language, so what we are trying to do is, so Qn n dimensional hypercube I can construct it using Qn minus 1 cross K2. So, when I say cross K2, there is a K2 structure sitting that connects two Qn minus 1s. Okay. So, this is the beauty of cross product. You will be able to see it as and when you just look into the structure, you will be able to see. So, what we are doing here is take two copies of Qn minus 1. You take the same labeling, n minus 1 bit labeling is there now, if you see, right. Look at the n minus 1 bit labeling. Oh, you guys can't see the colors in the label, sorry about that. Okay. So, if you look at this cube will be prefixed by 0, like the first bit is 0 for every vertex here and the first bit is 1 for every vertex here, and so you will be joining two vertices obviously if the bit differs by 1 bit position, right, that is the actual definition. So, here also we will do it in similar way. So, you will be adding the vertex 0 1 0 with 1 0 1 0 because only the first bit position will be differing. You join the identical nodes 0 1 0 to 0 1 0 where the first bit differs by 0 and 1. So, that is how all the connections are made. If you look at these two vertices, I have actually drawn this like a planar graph, so that you get a good feeling to see how this connection is made, right. Say for example, you can also look into this cube. Here also if you see, you have a Q2 and an outer Q2 is there. So, if you see all these outer cube will be having the first bit as 0 and the inner cube has the first bit as 1. So, I have just connected the corresponding nodes without disturbing the structure. So, in similar way we can just look at this as a recursive construction, okay, for Qn, where you take two copies and you construct it from two copies. This can also be taken down, instead of for Q4 I take Q3, I can also take 4 copies of Q2 and I can look at the corresponding 2 bit positions. Here also I can just do this, look at the first 2 bits. Okay, you will be connecting them if they differ in exactly 1 bit. So, I can go on and on like recursively, I can keep constructing them from just K2s. Take edges, take n edges and you will be adding corresponding the Cartesian product of n edges you are taking. So, you will have 2 power n nodes and then you connect the corresponding nodes in the fashion that we have told, right. So, this is the other beauty of this network. So, what can we say about the properties of this? Just by looking at this, can we say something? What is the degree of every vertex here? Degree of a node? 4, right. So, it is a regular graph. Hypercubes are regular of what degree? 4, that is n. If I am talking about Qn, I am talking about an n regular graph on 2 power n vertices. Think of it, that is the scaling that we are doing here. That is why this network was so beautiful, that you just reduce the network's degree by in log factor. You have 2 power n nodes, still you are connecting only to n nodes with every vertex, and the second factor, which is the next beauty, is diameter of this network. What is the diameter of this network? You take any 2 nodes, how much hops you need to connect them? N hops. Can all of you see this? See, suppose I mean, one usual example we take is, look at this, all zeros and all ones. These two are supposed to be farthest. Okay. So, you can just go from 0 0 0 to 0 1 to 0 cube 1, then go to 1 0 0 1 and 1 1 0 1 and 1 1 1. So, in 4 hops you will reach, right. So, if you look at this network, the diameter of this network is again n. Okay. This is the next beauty, that in log n hops, even though you have 2 power n nodes, you will be going down. If capital N is my number of nodes, log of that is only I need to reach any vertex. In log of number of nodes, I will reach any vertex in the network, right. Yeah, apart from that, we have also, I do not know if you can see the colors, it is a bipartite graph. You will never have cycles, odd cycles. So, you can see that it is going to be a bipartite graph, the way we have drawn itself, and I have given colors, I do not know if you can see it, there are blue and red colors. So, all blue color nodes form a partition and red color nodes will form a partition. So, yeah. Okay, actually none of my colors are shown here, that is a difficulty. So, okay, black and blue, that is at least a different contrast colors we have. Okay. So, if you want to also, there is also another way to look at this partition. If I give you any n dimensional cube, can you tell me what will be the partition without looking at the nodes? I know I give you hypercube, higher dimensional. Of course, after 4 it gets difficult to visualize it, like I have to take 2 copies of Q4, right. This whole structure I take 2 copies to get Q5 and I have to make connections, corresponding connections in that. Sometimes it gets out of your hands to visualize it. Okay. When I used to work on this, I used to draw up to Q6 by hand and practice to see, visualize the structure. Okay. But obviously it is not going to be easy. So, if I give you any n, can you tell me what will be the partition for this? Yeah, there are, it is an equipartite, so both the partitions will have equal number of vertices, but can you tell me which vertices will go into this partition? That is also staring at you. More than 1 bit, so can I put 0 0 0 and I will say 0 1 1 in one partition? Can I put that? See it, I mean at least in this you can immediately see that these two cannot go into the same partition. Okay. But in your binary labeling, you pull out all the nodes which has even number of ones into one partition and odd number of ones in one partition. So, that will obviously give you 2 hops, what you are looking for. Actually what we want to say is the difference should be at least 2 to come into one partition, right.